Okay. Hi, everyone. So thanks for being here. It's the second time for me at Black Hat and first time as a speaker. So today I'm here to discuss about machine learning and how we try to use it to enhance our detection capacity. So I'll start with a bit of context. Then I will explain the solution we have tested, the behavioral analytics solution. Before I'll try to explain the basic of machine and deep learning, and then I'll explain our use cases. So let's start with some context. So I'm part of Crédit Agricole, which is a French bank SOC team. So in Crédit Agricole, we have like 250K users within our information systems. And within the SOC team, we are collecting more than 300K events per second. So it's 10 terabytes of data, which are collected, parsed, and correlated in real time. So I guess that's nothing new, but just to emphasize that it's a lot of data, so it's almost 4 petabytes of data a year. And our role as the SOC team is to detect threats. So when I arrived like 4 or 5 years ago, I had to make sure we are at the proper level in terms of cybersecurity. And basically, we had been working with the MITRE attack to try and understand what we were not able to detect. And what we found out was it was kind of difficult to detect anything which were non-deterministic, meaning that we were great to detect things which were based on thresholds, but for anything else, we were struggling. So what came to our mind was machine learning. So machine learning has been famous for lots of time. It may not be really popular in our industry, but still it was famous, and we thought we should have a try and see whether it could help us or not. So the first question we've been asking is where we could have put some machine learning within our SOC. So in our SOC, we have like raw incidents that are being sent to our SIEM. So like those are like databases, server logs, etc. And we send the raw event to the SIEM. We also send some security solution events to the SIEM, and it does like the detection, and it sends the incident into our SOAR. So we could have put some machine learning at this stage, but the security solution already embeds their own models. So there is nothing for us to do there. We could also have put some machine learning to help with alert triage and prioritization, but our main goal was to try and enhance our detection. So we decided we would try to do something from the raw event directly and try to do some detection in terms of weak signals. So first, we didn't want it to reinvent everything, so we had been testing some solution, what I call like the AUTOMAGIC solution. And those have some advantages, like they are ready and easy to use. So basically, what you have, if you buy those solutions, you've been delivered with a server, and you just have to plug in within your network, and then it starts doing whatever it needs to do. And it's technology specific, which means those solutions are really well made for what they are supposed to do. So if you are willing to analyze the network traffics, well, it works great with pickups. But on the other end, like those solutions are not really flexible. So this means that when you buy the solution, you are being sent with a list of prerequisites you should achieve. And if you are not succeeding to achieve one of those, then you won't be supported. And in our big and complex information system, it was kind of difficult to have everything done. So yeah, that was something difficult for us. Also, we were concerned about confidentiality, because every time like, we had to send the data to the third-party vendors, and most of the time they were asking us to provide our data to their cloud. And we didn't want to do that. And we found it was kind of unfair because we were giving our data, but they were not giving us with their model. So it means, yeah, it was like an unfair situation. So we didn't want to do that. And also, those solutions were time-consuming, meaning it was really hard for us to qualify the detection and the incident we were having. At that time, we didn't know about explainability in artificial intelligence. But yeah, still, we were struggling to understand why an alert would have triggered, and we were giving no clue about it. So we decided we would jump by ourselves into machine and deep learning. So here, by raising hands, how many of you guys has already implemented their own machine or deep learning models? Yeah, okay. Quite a few, okay. So I will start by explaining quite the basis of it. Just here, just a bit of a disclaimer to say that what I'm going to show and discuss today is just our truth, so the thing we discovered by trying to implement our own machine learning, but I would be more than happy to discuss with you afterwards from what you think. So machine learning is part of artificial intelligence, and basically it can help solving two types of problems. So one is called the supervised problems, and the other one is unsupervised problem. So with supervised machine learning, basically you've got a bunch of data, and you've got a ground truth or a label associated with your data. And this allows you to do two kinds of stuff, like you can predict or classify the data based on the known label. On the other hand, like the unsupervised machine learning, you have the data, but you have no ground truth associated with your data. So you can still do something, like with unsupervised machine learning. You are able to do clustering, which basically is grouping the data together based on some patterns. And you can also do some anomaly detection, which means you can find the outlier within the data. So we worked with unsupervised machine learning because we didn't have any ground truth associated with our logs. So here, just an example of one algorithm which can be used to solve unsupervised machine learning and particularly anomaly detection. So this one is called the isolation forest. And the idea is you've got some data, and you say like an outlier is something which is different from the rest of the data, and you assume that you have few outliers within your data. And the main idea is you start drawing random lines within two thresholds, and the less lines you need to isolate a point, the more likely it is to be an anomaly. So we can see, for instance, that the point on the corner would be like more easily isolated rather than the point in the middle where there is less probability to draw some lines in there. So this is machine learning, nothing too fancy. Let's now have a look at deep learning. So with deep learning, you still have your data, which now is called the input data. And you initialize some random weights, and you start multiplying your data with those weights, and you add a bias. And this result is being sent to an activation function which normalized the data. And here you go, you got one neuron, and you iterate like for several neurons over several layers until you reach an output, which is your result. And basically here, what you are trying to do is you are comparing your output with your ground truth, and you are able to compute an error, like which is called a loss, the difference between your ground truth and what you get as a result. And thanks to an optimization algorithm, which is called the gradient descent, you are able to try minimize this loss, so you are able to reduce the error and approximate a better result. So you can, you can backpropagate the error and adjust your weights until you reach a good enough result. So here you should be asking yourself, like, how could we use this with an unsupervised problem? Because as we say, like, we have to compare our output with your ground truth. So how could we do if we do not have any ground truth? So there are different architectures in neural networks, and this one, which is called the autoencoder, could help us. Because basically, at the end, you are not trying to provide a prediction, but rather you are trying to reconstruct your input data. And you can still use the same mechanism as before, but that time trying to reduce the loss, so the error between your reconstructed data and your input data. And this is helpful because with anomaly detection, then, you can use this kind of encoded version of your data within the layers, which is called a latent space, as a representation of your data, and you can start using it and see if a new data looks different from that or not. So I hope you guys are still following and still awake. So here, what were we trying to achieve before I start this explanation? Well, we were trying to improve our detection capacity. So the use cases we focused on with my team was the exfiltration. So exfiltration is part of the MITRE ATT&CK matrix. And we could ask ourselves, why won't we use a DLP solution? Well, it needs lots of things to be done. And also, we are the SOC team, so our role is to detect things rather than prevent those from happening. So we believe that trust does not exclude control, so we are really willing to see what's going on within our network. So we decided we would still focus on trying to detect some exfiltration over the network. So the MITRE attack technique exfiltration, I've got lots of tactics associated with it. And if we have a look at the detection part, like the MITRE attack tell you, oh, you can try to detect stuff. Well, let's say you have to monitor the traffic and find something which is either like abnormal, anomalous, different, or suspicious. So we can understand that here we are trying to find non-deterministic behavior. So machine learning could be a great use case for us to help solve that. So what we did is we had followed like a machine learning or data science methodology. So the first thing we need to do is collect the data. So this could be tricky sometimes, but we are the SOC team, so we already have the data. We decided we would work with the proxy logs rather than with the network traffic because it was easier for us. So we start from there. Then we had to clean the data. So the idea is to remove all the unnecessary part of the data. For instance, we have removed the proxy logs from the logs themselves. We only kept the traffic from the company to the internet. Then there is what's called the feature engineering part. So here we computed some interesting variables about our data, and I will explain this a bit further. Then there is the modeling part where we do the machine learning, and then we predict a score, an anomaly score, based on our data. So let's see the feature engineering part. So here is a sample of proxy logs. So we can see we have lots of metadata associated with it. In green, the metadata can be used to detect like if there is a huge amount of data which are uploaded to a domain. So we can, with those, detect like huge exfiltration, mainly based on thresholds. But we found out that there are lots of other metadata that can be useful to detect things suspicious, like the user agent, the response code from the server, the proxy, the action would have taken. So yeah, we decided those metadata could be useful. So we worked with 15 days of data for our prototype, and we used like almost 15 gigabytes of data. And the first thing we had to answer was how we should represent our data. So here, I'm making a bit of interaction with you guys. How many branches can you guys see on that picture? I guess it depends on perception, like 4, 3, depends. So yeah, it depends on perception. And the thing I would like to emphasize here is the way we represent our truth, our reality, would impact the way we are trying to solve our problem. So what we decided was one log cannot be considered as threats, but we could have worked with multivariate time series and try to detect anomalies within those, but this would mean we would have worked with so many time series. So what we decided was we would work with an aggregation. So basically, we came from the unitary logs, and we aggregated those into daily behaviors. And from that, we start computing some indicators. So the first type of indicators we've been computed was some like the total number of requests which were made by that machine, the number of volumes that were uploaded to that website or to whatever website from that machine, the ratio between HTTPS and HTTP requests, also the number of unique user agents the machine would have, the number of IP addresses that were requested instead of domain. Then we have computed more generic features like what we call the popularity. Basically, we had counted the number of unique users which had requested a website. So if all of our users were requesting a specific website, well, it's likely to be something normal. But if just a couple of users are going to a website, maybe it's something which can be suspicious. So we were aggregating the data daily, so we were removing the domains part, but still we were able to count the number of kind of unpopular domain a machine would have requested. we also have done some profiling. So we have used like clustering algorithm within our data, and we had counted the number of time a machine would have changed from a cluster to another. Also, we had computed the distance from that particular point to the centroid or to the nearest clusters. And also, we have computed some evolution indicators. So basically, the idea here is to say, like, if a machine is doing a lot of requests, but it's normal behavior, well, there is no point to detect it as an anomaly, like, every day. So, yeah, those are the features we've been computed. So here, the thing is, there is strong mathematics associated with machine learning, but also, on the other end, we have to make sure the data we are feeding it is nice. So yeah, I just want to emphasize that the knowledge of the data is something which is also really important in machine learning. So then comes the machine learning parts. So here we can see like it's like 10 lines of code. We define our model, we train it, whereas what we just saw was like 500 lines of code. So it just proves what I just said. So here what we do, basically we pass our data, we initialized our model, which is the isolation forest we discussed a bit earlier. And then we train it. We are missing few regularization parts here, but just this is the main idea. And yeah, you just like predict an anomaly score based on that. And here we see like the contamination ratio. So in a way, we reintroduced some threshold because we say like we would like to see 0.5% of our data set as an anomaly. Here we did that because we did not want to send too many alerts to our analysts, so we had to reduce the efforts. And once we've done that, so basically what we had was like a daily behavior, an IP address, and then an anomaly score. And when we came to our analysts, we were like really proud of what we've done. But they were like, okay, so you've done some machine learning, but all I can see is CSV files, and there is no way we would work with CSV file. I guess they are used to more fancy stuff. So we had to figure out a way on how to make them use what we've done. So in unsupervised machine learning, there is a third type of problem we can solve, which is like dimensionality reduction. So there is a technique which can project your dimensionality within lower dimension. So we had computed like 71 variables, and we projected those into 3 dimensions just to make things a bit more interactive. So we had then developed like a tool so we can review our anomaly. So here we can see there is like the daily behavior, which are plotted into 3 dimensions. And it's kind of intuitive that the points which are different are the anomaly. So you can start clicking on those, and you can review the daily behavior associated with that point and all the behavior of that particular machine with the anomaly score, and also like everything we have computed and everything we found relevant to provide to the analysts. And when we click on that particular point, then we can review all the domains, like all the unique requests which were made on that particular day. So I've anonymized the domain because I just want to make it that like this. And then we can provide us with a feedback. So you can say whether like this behavior is an anomaly or not, like it's a false positive, it's a true positive, it's something interesting, whether we need to whitelist the domain or the machine. And also we are able to generate an Elasticsearch link, because basically what we've done is we send those results, like all those features we've been computed, to our Elasticsearch, and together with the raw events, we are correlating those to enhance and provide more information to the analyst. So the main idea was to make sure we provide everything we can to the analyst. So we used basically statistics to provide whatever could be of an help for them. But we didn't want it to automate their job. And as we just saw, like basically what we are detecting are more like weak signals, and we really need analysts to work on those suspicious activity. So I guess you've the idea of what we've done, and maybe you should ask yourself now if it's working. So let's try to see whether it works or not. Okay, so in order to understand whether what we've done is working or not, we should understand how we are trying to evaluate things. So with supervised machine learning, well, you've got your prediction, but you also got your ground truth. So it's kind of easy because you can compare your ground truth and your prediction, and you can start computing some metrics like the precision and recall. If you are working with unbalanced data set, we have to make sure we are using the proper metrics, but still you have something to rely on. On the other end, with unsupervised machine learning, it's kind of more difficult because you cannot compare your result with ground truth. So still you are able to compute some metrics like the distance between and within the clusters. You can compute what's called the silhouette score. But I guess that's enough of mathematics. And what we really want to say is whether we are able to detect real threats. So what we've done is we had worked with empirical evaluation. So we have been implementing our own simulation to make sure we would detect those. So here, what we can see is some daily behavior, as what we saw before. And within those data, we have some simulation we have implemented. So here we have a number of behavior, like 30,000 behavior, more or less. And the number of anomaly, like the total anomaly, which were found by our model was like a bit more than 2,000. And within those, we had put 0.5% as the top anomaly, which can be reviewed by the analysts. And what we can see is like in blue, orange, and green, we have projected our simulation. So we have defined like 3 types of exfiltration we would like to detect. So the first one is what we call the scheduled data transfer size limit. So basically, we just chunk data and send those to a servers in an automated way, so in a regular basis. We also have worked with what we call the exfiltration over specific channels. So basically, just communication through a normal or like a suspicious server. And also the subdomain exfiltration. So here is not like DNS, proper DNS exfiltration, because we were working with the proxy log. So it's just like we passed the data within the subdomains, but in an HTTP request. And in gray, it's unlabeled data. So what we can see is that the simulation we've made are part of the anomaly we found, and we can see they are kind of different from the rest, mainly. So this means that we found some relevant features that allow us to like detect those behavior. And yeah, in gray, there is one guy which is doing random stuff, like which is not part of our anomaly or our simulation, but may be reviewed. So just to provide a couple of stats, so we have iterated like a couple of times, and in this example, like we have done like 20 tests of each. So it's like 60 simulation over our 30,000 behavior. So it's quite very few. But we can see that with the all isolation forest detection, we were able to detect lots of the things we've simulated. And still, with the top 0.5% of the anomaly, we were able to detect some of those. With our legacy detection system, we were not able to detect any of those behavior. And one day, I arrived at the office, and I was reviewing the anomaly as part of my daily job. And I found out that I was the top anomaly of my model. So I just asked myself, what did I do? So we had a look with my colleague, and what we understand is I was booking my tickets through the Eurostar platform to come see you guys. And the Eurostar is sending lots of messages to the Sumologic website. So basically, it's a tracker. So we can see like in 20 seconds, there is like more than 300 requests being made to that third-party website. So obviously, I found myself as an anomaly. Because, yeah, basically, a tracker has the same similarity between the scheduled data transfer we tried to detect. So we ask ourselves how to prevent those to be detected, and how can we differentiate a real exfiltration from a tracker. And the only thing that we found out was based on the domain. So what we did is we used some domains features. So basically, we reduced the job we've done on the daily behavior on the domain parts. And we had added some more features, like based on the whois, like since when the domain was online, and like the classification of the domain, and lots of things like that. And we are convinced that this, correlated with what we've done before, would help to reduce the false positive. So yeah. So let's see how then some limitation and perspective on what we did. So with our machine learning custom development, we were able to leverage our detection capacity, because as we saw, like, we were able to detect more typology of exfiltration than before. Also, what we made was really flexible, so we were able to adapt it to our context. We are able to whitelist things and to build our own features and to make those available for the analysts. We can explain why this would have triggered and etc. But it's still time-consuming because we have to implement everything. And also, I'm convinced that we cannot add some detection, reducing the analyst time. So yeah, for sure, we need people to review the anomaly we have detected. And we need resources, we need people who develop and maintain what we've done. But our main goal was to leverage our detection capacity, so I guess we had succeeded in that way. So just a couple of takeaways. So here we were able to enhance our detection capacity using data sciences for sure, but mainly using the knowledge we have on our data. Just to keep in mind that we are dealing with weak signals, which means that we can use what we've done either as a threat hunting approach or with like our legacy detection, like to contextualize the legacy detection. Like if we have an incident on a machine, we can check and see whether it's something which sounds suspicious from our perspective as well. So yeah, I believe if we have Python, face, and willing to do stuff, we can do great stuff using statistics and those kind of techniques. In terms of perspective, we would like to industrialize things. So for now, things are automated, but they are not industrialized in a way like we are not reviewing the inference of our model. We are not monitoring it. We would also like to improve the reproducibility. So we are able in our own information system to make things reproducible. But I would like what we've done to work with different type of proxy technology. So yeah. And also we would like to try use some deep learning techniques. So we had tried to work with some autoencoders, as I showed you at the beginning. And those looks to provide nice results. So we would like to deep dive into that and maybe use it in our production. And yeah, for sure, we'd like to implement some new use cases and correlate those with what we've done so far. So just some final words to say that, yeah, the main idea here was not to say this is how you should do stuff, but rather to say, like, this is the path we had followed, this is what we found on our way. And if you guys had any remarks or anything, I'm convinced we can do great stuff, but it will be even more effective if we discuss together. So that concludes my talk. I'd like to thank all those guys that were involved. And if you have any question, I'd be happy to try and answer those.